Hi everyone, welcome back to another session on the discussion of set theory. In the previous class, we discussed about definition of set and even how to represent a set. We learned there are two methods, that is roster method and set builder method. We even learned how to convert from one form to another form. In this session, we will learn about the types of sets. So first of all, we will learn about null set. What is a null set? A null set is a set which contains no elements, or you can say a set which does not contain any elements is called null set. It is also called as void set or empty set. The meaning remains same. To represent a null set, we normally use two kinds of symbols. One is phi, that is a Greek letter. It's like a circle with a vertical line in between, that is a letter phi. Or we can use empty braces like two flower brackets without anything written in between. These are the two symbols we use to denote a null set or an empty set. Examples of null set. Let us see which type of sets can be called as null set. See, first of all, set means it is a well-defined collection we said. Then there is a confusion that a set which does not contain any element. In that case, how can we call it a set? Say, for example, let A be a set of all x such that x lies between 1 and 2 and x is a natural number. I have defined it probably perfectly. Now, if anybody tries to answer this, they have to come up with the same answer. The solution remains same. In that case, it is well defined. But if you check the number of elements inside, there will be nothing. See, there is no element x, which is a natural number and which is between 1 and 2. Because in natural number series, if you check, first is 1, after that comes 2. In between them, there is no other natural number. So obviously, the elements in this set A is nothing. We can't even write 0. If you write 0, then it itself becomes one element. So if you write flower bracket 0 flower bracket close, then it is not a null set. What is that set called? We will discuss in the next slide. Now, another example. B is a set of all x such that x square minus 2 is equal to 0 and x is a rational number. See, B is again an empty set or a null set. Why? See, let us try to solve the equation x square minus 2 is equal to 0. Right? Minus 2 goes to the other side. Take it to the right hand side. What does it become? Plus 2. So now how does the equation look? X square is equal to 2. If you are getting doubtful about this, it is better if you write on a piece of paper. X square minus 2 is equal to 0. Minus 2 goes to the other side, becomes plus 2. We write x square is equal to plus 2. Then, in order to get the value of x, take square root on both sides. So, x square becomes x and the root of 2 remains as plus or minus square root of 2, because every quadratic equation has two roots. So, similarly here we get two roots, plus or minus root 2, and you know that root 2 is not a rational number. Root 2 is an irrational number. Hence, these two values, irrational values, they cannot be used here because we have already defined x is a rational number. There is no rational number which can satisfy this equation. Though it is well defined, everybody will have to come up with the same answer, that is nothing. So, B is again a null set. One more example. D is a set of all x such that x square is equal to 4 and x is odd. See, that cannot happen because if the equation x square is equal to 4, if you simplify that, you will get x is equal to plus or minus 2. If you take square root on both sides, you will get x is equal to plus or minus 2. But both the answers, plus 2 or minus 2, they are not odd. Neither of them will become odd. Because of that, you will not find any other odd number which will satisfy this equation. So, the only possible roots remain Nothing. So D again contains no elements in that when we write it in the roster form. Though we can define all these examples in set builder form, when you write in roster form, there will be no elements in it. So the best way to identify a null set is writing it in a roster form, because in set builder form they all contain one or the other property, but when you check the elements, there are no elements. Hence these are examples for null set. The next kind of set is singleton set. The definition for singleton set is the set which contains one and only one element is called a singleton set. Example: A is a set of all x such that x is a multiplicative identity. Here we are discussing about basic operations of multiplication in sets like natural numbers, whole numbers, rational numbers, irrational numbers and real numbers. We are not discussing about special topics like matrices and vectors. See, when we come across those chapters in your future, you will find that there are other multiplicative identities. But till now what we have studied, applying that knowledge, we will find that there is only one multiplicative identity in multiplication and division, and that is 1. So this set A will contain only one element, that is the number 1 itself. So this is an example for singleton set. Second example, B is a set of all stars in the solar system. In our solar system, there is only one star, that is the sun. Of course, there are other stars in our galaxy and in our universe, but when we are discussing about our solar system, there is only one star, that is the sun. Hence, this is an example for singleton set. Third example, set C is equal to set of all y such that y lies between 1 and 3. Here 1 is strictly less than y and y is strictly less than 3, and y belongs to n, that is natural numbers. We know that natural numbers are written as 1, 2, 3, 4, etc. continuous. But if you check which element lies between 1 and 3, there is only one element, that is 2. So because of this, C is an example for a singleton set. Next example, D is equal to set of all x such that x square minus 6x plus 9 is equal to 0. If we factorize this, further if you want you can take a piece of paper and solve this. It goes like this: x square minus 6x plus 9 equal to 0. Next step, x square minus 3x plus 9 equal to 0. Further, x is taken common outside, x into x minus 3 plus 3 into x minus 3 is equal to 0. Again, factorizing further, you will get x minus 3 into x minus 3 is equal to 0, or x minus 3 whole square is equal to 0. Simplifying, you will get both the times the same answer, that is plus 3. Instead of getting two distinct answers for this quadratic equation, you will find the same root repeated twice. So if you write it in roster method, D will look like a singleton set because there is only one element, that is 3. Coming to the fifth example, E is equal to, it is written in this roster method, between the braces we have written 0. So 0 is not a null set here because within the flower brackets there is one element. That element is 0. So though 0 does not have value while calculating, while adding or subtracting, here 0 is itself an element. So it doesn't matter about its value, whether you write there 9 or 6 or 1 or 0, all of them are considered to be one element there. Any single digit is one element. Hence, this is not a null set, but it is a singleton set. Next kind of set is finite set. What is a finite set? A set in which the number of elements, if you can definitely count it, if it is a definite number, then such a set is called finite set. We can rephrase the same. A set which is empty or consists of a definite number of elements is called finite set. See here, that word empty is important. An empty set is also a finite set because you can definitely say there is 0 elements. So perfectly you can name the number of elements. So empty set or null set is also finite set, or any other set where you can strictly count the number of elements or definitely say the number of elements, that is called as finite set. Examples for finite set. First one, set of days of a week, that is equal to Sunday, Monday, Tuesday, Wednesday, Thursday, Friday and Saturday. There are 7 days. You can count them and definitely say that there are 7 elements. Even if it's a big set, even if there are crores and crores of elements, it's okay. But if you can count them properly and say definitely how many numbers are there, then it becomes a finite set. Roots of a quadratic equation. See, roots of a quadratic equation can be either a single root or a two root. A maximum of 2 roots, not more than that. So definitely you can say it consists of 1 or 2 roots. Then it is called as a finite set. Third one, names of students in your class. Now, if you make a set of all the names of the students in your class, you will surely know that how many number of students are there in the class. Since the number is definite, this is an example for finite set. Fourth one, factors of a composite number. Let us take an example like 6. What are its factors? 1, 2, 3, 6 itself. So we have 4 factors for this composite number. So since I can definitely say the number of factors, it is an example for finite set. Even if the number is a very big number, maybe crores or bigger than crores or tens of crores, that number will have a definite number of factors. Yes, there will be a lot of factors, but the number of factors will be definite. So since the number of factors are definite, it is called as a finite set. Fifth one, natural numbers between any two numbers a and b. So let us take any two numbers a and b, like it may be rational number or real numbers, any numbers. Let me take some example like 1.5 and 2.3. Now if I try to find out natural numbers between two real numbers or rational numbers, for example, as I told you just now, you will find the number 3 in between, right? If I take another example of 0.01 and 0.02, see, there is no natural number lying between these two numbers. Therefore, it will be a null set. However, look at the definition's first line. If a set which is empty, so null set is also finite. So this example which I just spoke about is a finite set. So no matter which two numbers you take, it might be complex numbers or real numbers or rational numbers or irrational numbers. For example, which numbers come between root 2 and root 5? So root 2 is 1.4 and root 5 somewhere 2.25. So if you find out which number lies between both of them and it's a natural number, the answer will be 2. So it is a finite number. You know there is only one element like that. Hence, this is an example for finite set. So the types of sets we have already studied are null set and singleton set. They also are examples for finite set. So here it is. The next example is null set itself, which is a finite set. The opposite of that, or contrary to the previous one, is infinite set. Obviously, the definition is also the contrary of that. A set which contains of an infinite number of elements is called infinite set. So examples for infinite set, where you cannot definitely say how many numbers are there. Set of natural numbers. See, natural numbers, you know where to begin them or where to start. That is 1, 2, 3, 4, so on. But you never know where it stops because we are not definite about the number of elements. Such an set of elements is called as infinite set. Set of prime numbers. We of course know where it starts. That is 2, 3, 5, 7 and so on. But we don't know where they end because there is no end for prime numbers. Hence they are called as infinite set. Set of real numbers between any two numbers a and b. Let me take two simple numbers like 3 and 4. If a is 3 and b is 4, let us try to understand how many real numbers are there between these two. So between 3 and 4, you have 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9 and 3. That is 4 next. So you feel that there are 9 numbers. Are the only 9 numbers real numbers there? No. Between 3.1 and 3.2, again you have 3.01, 3.02, so on till 3.09. Between 3.01 and 3.02, again you have 3.001 and 3.002, so on like 3.009. Again, between any 2 points there, you will get 3.0001 and so on till 3.0009. This process can continue without end. So you cannot say how many real numbers are there between any 2 numbers. So it is an example for infinite set. Multiples of 3. So what do you mean by multiples of 3? See, 3's multiples start with 3, 6, 9, 12, so on. But we do not know where it ends. Hence, it is an indefinite series of numbers. We can call them as infinite set. Another example is integers greater than 5. See, integers, they proceed on both directions, positive as well as negative. Greater than 5 lies to the right side of 5, that is 6, 7, 8, 9, so on, but there is no end. Hence, it is an indefinite series of numbers. We call them as infinite set. One more example. X is a set of all x such that x greater than 10 and x belongs to whole numbers. So whole numbers starts with 0. So 0, 1, 2, 3, 4, so on. And if you consider all the numbers greater than 10, that starts from 11, 12, 13, 14, so on without any end. So there is no definite number of elements. We can say that it's an infinite set. Continuing the discussion, it is not possible to write all the elements of an infinite set because there are so many elements. And infinite also means uncountable elements, so many numbers of elements. Actually, as you further study for your future studies, you may come across definitions for different for uncountable and infinite set. For the moment, we will consider both as same. So elements of an infinite set within braces, that is within flower brackets, it's impossible to do that. So what we do is we represent that set with few elements clearly indicating the structure of the set, followed by 3 dots. Let us see what this sentence means. See, multiples of 5. We will try to indicate this structure by few numbers which will show you the idea or the structure of the numbers like 5, 10, 15, 20. Obviously, we can guess the next numbers 25, 30, 35, 40. Yes, the structure we understood. The property we got it. But we cannot go on writing it till the end because there is no end for this. So just to show that this continues, before closing the braces or the flower brackets, we put 3 dots there. These 3 dots indicate that it goes on or so on without end. So all infinite sets cannot be described in the roster form. We just discussed that you can write the roster form as few numbers indicating the structure and then 3 dots. But this does not apply for real numbers. See, in a set of real numbers, if you consider, what will happen is those all elements are so different. They all do not follow one same structure. So it is not possible to note down all real numbers. Just have a look at this picture that comes on the screen. See, the numbers are so different and in between there are so many gaps which can be filled with again innumerable numbers. Any 2 numbers if you consider in this, they will contain again indefinite number of elements. Hence, this cannot be written in a common structure. So for real numbers, we will have different kind of notation which we will study in the later part of this same chapter. Next topic of discussion is equal sets. What are equal sets? 2 sets A and B are said to be equal if they have exactly the same elements and we can write it as A is equal to B. So let us go by the example. First example, let A is equal to 1, 2, 3, 4 and B is equal to 3, 1, 4, 2. Now, though the order is not same in both, all the elements in A are the same elements which are there in B. Have a look at the elements. 1, 2, 3, 4. Do we find 1, 2, 3, 4 in B? Yes, in a different order, but the same elements. Is there any element in A which is not there in B? No. Is there any element in B which is not there in A? No. So that shows that all elements of A are present in B and all elements of B are present in A. Thus, we can say A is equal to B. Let us consider three different sets here. P written in roster form. P is equal to set of 1, 2, 3. Q is set of all x such that x is less than 4 and x belongs to natural numbers. And R is set of all x such that x lies between strictly 0 and 4 and x belongs to whole numbers. Then we can say that P is equal to Q. How is P equal to Q? They don't look same. But because Q is written in set builder form, if you convert it into roster form, which are natural numbers less than 4? 1, 2 and 3. The same elements which are present in P. Therefore, P and Q are equal. What about P and R? Here we have written P is equal to R. Look at R. R is a set of whole numbers between 0 and 4. Which are the whole numbers between 0 and 4? 1, 2 and 3. Again in roster method, the numbers are same 1, 2 and 3. Therefore, P and R are equal. Compared between Q and R, though the structure looks different in the rule method or set builder method, the sentences are different. But in roster method, both of them will have the same answer, that is 1, 2 and 3. These are the elements. Hence, Q and R are also equal sets. A set does not change if one or more elements of the sets are repeated. You remember this? Because of which, what happens is, in equal sets sometime, if one of the sets is written with more number of elements, but not having any distinct different elements. Example C. In the first example, A is 1, 2, 3, 4. B if I write as 3, 1, 4, 2, 3. Again, if 3 is repeated, it looks like it has 5 elements. 5, but it is not. Because 3 has been repeated twice. Only the distinct elements, if we check, they both remain same. So, we need to remember. Therefore, set A is equal to 1, 2, 3 and set B is equal to 2, 2, 1, 3, 3. They both are equal because distinct elements are only 3 of them. Some of them are repeated. That's why. Distinct means those which are not repeated, which are particularly separate from each other. Unequal sets. The next example is unequal sets. What are these? Say they are the contrary or the opposite idea of equal sets. If the elements of A and B are not exactly the same, then the sets are said to be unequal. We write them as A not equal to B. So what do you mean by that? See, either A or B should contain one element extra or one element lesser. Sometimes both may have the same number of elements, but if one element is different, then they both are unequal. Example, let us see. Here A is 1, 2, 3 and B is a set of 2, 3, 4. See, at first look or first glance, they both have the same number of elements, 3 and 3. But are they same? No, because in set A there is 1 and 1 does not exist in set B. And 4 belongs to B, but 4 does not belong to A. Then we can say A is not equal to B. If C is a set of 0 and 1 and D is set of 1 and A is set of 0 and F is a null set, then see, let us compare. There is a bit of confusion that can occur here. So be careful with each comparison. C not equal to D because C and D. C contains 0 and 1 whereas 0 is not present in D. If even one element does not appear in another set, automatically those two sets are not equal. How about C and E? Again the same. C contains 1 but that does not exist in E. Therefore, they both are not equal. How about C and F, the first one and the last one? Of course, they are not equal because C has two different elements, that is 0 and 1, while F has nothing. Automatically, they both are not equal sets. Let us compare between D and E. They both appear to be having the same one element, but no, the elements are different. The elements are not the same. One is there in D, but one does not exist in E. 0 is there in E, but 0 does not exist in D. Therefore, D and E are not equal. How about D and F? See, D contains 1, but F is a null set. So, D is the element of D, which is 1, does not exist in F. Therefore, we cannot say that they both are equal. We can say they both are unequal because elements are not same. Last but not the least, how about E and F? E contains 0, F is null set. Though at broader look, they both look same, they are not because E contains one element, F contains no elements. Instead of saying 0 elements, we will say no elements. Because 0 itself is an element, it gets a bit of confusion. People get confused when we discussed about E is equal to 0 and F is null. They both look same but no. E is a singleton set because it contains one single element called 0. However, F is a null set because 0 does not exist in that, because of which E is not equal to F.